coffee. Now, I like to hand over to our next presenter. Here is Dr. Arthur Mutter. Dr. Arthur Mutter studied mechatronics at the University of Stuttgart. 2012, he finished his PhD in the area of communication networks. The topic of his PhD thesis was the memory architecture of high-speed routers with more than 100 gigabit per second per port. Since 2010, Dr. Mutter works at Robert Bosch GmbH in the area of hardware IP development. He was significantly involved in the development and standardization of KNFD. Currently, Dr. Mutter is responsible for the standardization of KNXL, and since 2018, he is chairperson of the special interest group KNXL at Canon Automation that specifies the KNXL data link layer, physical layer, and higher layers. Today, Dr. Mutter presents to us the KNXL error detection capabilities. So thank you, Dr. Mutter, the stage is yours.
Rainer, thank you very much. Now I figured out how to show myself on the video. Now, okay, I'm fitting into the screen. Thank you very much. Okay, so I will start my presentation with a short story. So when you imagine you want to buy a car, let's say today we want to buy an electric car, then you will start comparing features. We will start comparing the battery capacity. We will look for the range of the car. Since it's a fan factor, we will look really deep on the acceleration. And if you're looking for a family car, you will even check the trunk volume. You will maybe have a look at the brand reputation, for sure on the price. So these are all things you will look on. However, it's really unlikely that you will start counting the airbags in the system and the other safety measures of the car. And this is because you implicitly assume that the car is safe and will protect you. And the same is the case actually with communication technologies. We typically compare the max bit rate, the payload size, the maximum, for example, in KNXL 2048 bytes. We will take a look at what topologies can be supported, how many nodes can I connect, what is the price, are there different transceivers, and so on. It's really unlikely that somebody will start comparing the error detection mechanisms of two systems. Maybe somebody does, but usually people don't do that. Because we implicitly assume that error detection is present and will work properly and will protect us from receiving erroneous frames, right? Nevertheless, sometimes we need to talk about the topic, and this will be today. And I will show in my presentation today what effort we've made in the standardization or during the specification of KNXL at Canon Automation to bring a really good error detection into the KNXL protocol. Now, let's get into the car and let's see what happens on a bus. So a deeper motivation follows now. Now let's take the laser pointer. Okay, so when we take a look on the wires, like done in the presentations already before, then we see a waveform, right? And this waveform may be disturbed. And the disturbance may be an electromagnetic radiation, because a car or the environment where the car drives may be a harsh environment, maybe not always, but sometimes. And this disturbance modifies now our waveform. This means that the physical coding sublayer in the receiving node that converts, this is the piece of logic that converts the waveform into individual bits, so it samples the data. And this PCS sublayer will then convert the bus signal into an erroneous bit sequence. You see it's marked here with a red bit flip, bit error. So due to disturbance, we will see a bit flip here. And now this bit stream is handed over to the medium access control. And now we expect from the medium access control that he detects the error, because this is his job. He has measures to do that. And detecting errors gets more and more important because we build more and more safer systems. We head towards autonomous driving vehicles, and therefore safety is very important. And therefore we expect from the Mac that it really detects nearly all errors. There's always some residual error rate, but we want a good job from this Mac layer. And when we build now a robust and reliable system, we need two pillars, otherwise it will not work. The one pillar is the error detection itself, and the other pillar, the error handling. So you need to detect an error, and then you need to react on that error. You need always both. And as you may know, the error handling in CAN-XL, there are two flavors of it. So we can have the error signaling enabled, then the error handling works with error frames. It's identical to CAN-FD, but we can also have error signaling disabled. Then we do something different. But however, this is not the topic of today's presentation. Today, we will have a look exclusively on the error detection. And error detection in CAN-XL means we have three mechanisms to detect errors. These are three completely different mechanisms. The one mechanism is format checks. That means we check the format. The second one is CRC checks, so cyclic redundancy checks. This means this is some mathematical stuff. And finally, we have the bit monitoring. And bit monitoring means the sending node checks his own bits if they appear on the bus. However, bit monitoring is only present if we have the error signaling enabled. And now, since you know the expressions and the topic, I will now head on to the agenda. So first, what we will look at will be the error types. So what is our threat? And these are the error types. We will look at it and we will just learn what types of errors are out there in literature and described. Then second, I will present the error detection capabilities we have built in CAN-XL. And this will be the CRC concept. And then I will also show a delta view between CAN-FD and CAN-XL, and will show how we improved the good error detection of CAN-FD to an even better one in CAN-XL. And finally, I will show some evaluation, because the best error detection is worth nothing when you do not evaluate it, because you need to be sure that it works. It's not just a feeling, we need to really know that it works. Okay, then let's start with the error types. So basically, we have three types of errors in CAN, known from literature. The simplest one and the most common one is the bit flip or bit error. These two names are just synonyms. And as you see it here, the sending node is sending a 0 and a 1, then 4 zeros, and then a 1 again. And you see the receiving node receives bit number 3 as a 1, even if it's a 0. And this is a digital view here. This is the view of the MAC layer for sure. When we would look on the waveforms on the bus, there would be a glitch somewhere, and yeah, it would look different. So there is not such a perfect bit flip. The second type of errors, which was, I think, first mentioned in 2015, is the so-called bit drop or bit insertion. This type of error was at that time called fault type B. So maybe somebody remembers. So actually it's a bit drop or bit insertion. What does this mean? A bit drop means that, for example, we send the following bit pattern, a 1, 5 zeros, and then a dynamic stuff bit. And the receiver sees a 1, 4 zeros, and a regular 1. And how can this happen now? And here you see an example how this can happen. You see the sending node is sending this bit stream, and the receiving node receives a signal that is falsified. You see this red area is new here. So the edge on which the receiver synchronizes is shifted. So that means the receiver synchronizes on a wrong edge. So instead of correcting a phase error, it even increases his phase error. And as a consequence, with such a big phase error, these blue things are the sample points. You see it samples the bit stream, and then it samples the following stuff bit instead of the bit number 5. And therefore, he just skips or drops one bit. The same can happen in the opposite direction. Then we call it bit insertion. And that means actually we send a 1 with 4 zeros and then another 1, and the receiver may see a 1 and then 5 zeros. And this can happen when the error occurs in the other direction. So we move this edge where the receiver synchronizes on to the left, and we shift the view of the receiver to the left. That means we pull in the sample point of bit 5 into bit 4, and then we sample the 0 here instead of sampling the 1. And what is important now to know is, yes, bit insertions and bit drops can happen. Nevertheless, we need a lot of preconditions. We need bad oscillators. We need multiple glitches and so on. We need bad configured sample points and so on. So it's not easy to produce it, but they are absolutely realistic, but not easy producible. That's the message. And as last category, the third one, we have burst errors. Burst errors, there are two types of them. The ones are where the bits are flipped in the data stream. So I send 101010, and I receive just flipped bits. And the other type of burst error is when I force all the bits for a specific duration of time, for a specific time duration to a constant value. Here in this example, I force the bit values to the value 0. And you see then 2 bit flips appear. Okay, now we know the error types. Now let's head on to the error detection capabilities in CanExcel. How do we solve to detect these errors? Because we need to detect them that they happen. And what is important to understand now, that the CRC check, so the cyclic redundancy check, this mathematical stuff, is the core of the error detection. This is the absolute core, and we need to protect this core. So we need to make sure that the CRC check can work, can do its job. And to enable the CRC to do its job, we need to fulfill some requirements. In other words, to be able to rely on this 100% on the CRC's error detection capability, we need to make sure that the transmitter and the receiver of the frame calculate the CRC sequence based on the equal number of bits. So if the sender sends 1,000 bits, then the receiver needs to calculate its CRC also on 1,000 bits. If he counts it on 999, the CRC check is worth nothing. Then it's a random. So we need to make sure that this works. Second, we need to make sure that the receiver checks the CRC sequence at the right position inside the transmitted frame. So that the receiver needs to sample the CRC bits transmitted at the right position and not in the middle of the frame where it's wrong, right? So we need to make sure. And the last thing is has something to do with dynamic stop bits. So the CRC, we need to make sure that the CRC check is not compromised by errors in combination with dynamic stop bits. Because dynamic stop bits can be there, but also not. A receiver can not judge if it was there or not. So we need to protect the CRC from dynamic stop bits that may be missing, for example. And now on the right side, I will show you the measures, how we manage to fulfill these requirements. And to fulfill the requirement that we check the same number of bits in sender and receiver, we took two things. First, we use fixed stop bits instead of dynamic ones, because with fixed stop bits, we have a fixed frame length, right? There is no tolerance, no misinterpretation. It's totally clear what has to receive. And the second solution or second measure, we not invented, but we introduced a prephase CRC to safeguard the data length code field. That means the data length code field contains the length of the data field. So for example, 1000 bytes. And when we protect this DLC field, then we for sure know where the frame CRC will be. And we can then sample it at the right place. Regarding the position of sampling the frame CRC, we also have two measures. The one is that we added a so-called format check pattern, a so-called FCP field. What this means will be shown on the next slide. And also the data length code helps here to sample the frame CRC at the right position. And then finally, to deal with the dynamic stop bits and the errors in combination with that, we do the following. We include the dynamic stop bits into the PCRC calculation, but exclude them from the FCRC. And by this, we can cover all the cases and everything is fine. So now let's have a detailed look on the format check pattern. How does this work? How does this make sure that we sample the frame CRC at the right position? Now, here you can see a kind of the MAC frame format, and you see here the transmitted bits. And you see at the end of the frame, after the frame CRC, there is a field called FCP, frame check pattern, or format check pattern. And this field is a constant field, always with 1, 1, 0, 0, never something else. And now let's have a look at the receiver. And in this example, I have drawn here two lightnings, and there's two disturbances. And these two disturbances, let's say they are glitches, lead to two wrong synchronizations in the receiver, in the receiving node. And that means due to these two wrong resynchronizations, not the synchronization is wrong, I'm sorry, the edges are wrong on which we resynchronize because the edges are disturbed. So due to these two wrong edges, the receiver will drop 1, 0. And when it dropped 1, 0, you see the whole bit stream is shifted for the receiver. It just misses 1 bit. This means the receiver will sample the frame CRC 1 bit shifted. Additionally, it will have 1 bit less. So the content of the frame CRC is not mathematically provable now. It's just random if it's correct or not. There is no theory about this case. That means we need another protection. And the protection is the format check pattern here at the end. You see the format check pattern also shifted. So the format check pattern is now 1, 0, 0, X. We don't know what will be here because the physical layer switches here back. So it's random. Anyway, we see the FCP is unequal 1, 1, 0, 0. So the receiver will be able to detect with 100% this shift. And what are now the general capabilities of the FCP? These are, it detects with 100% probability unlimited bit drops. That means we can shift this bit stream to the left as long as we want. We will always detect it because on the right, mostly ones come. Or it will also detect up to 3-bit insertions. And this 3-bit insertions is much. When we assume that 1-bit insertion is like 2 or 3 bit flips, then we would detect up to 9 bit flips. This is enormous. So this is much more far than we need to go, because the typical standard is 5 bit flips need to be detected typically, because then we get a residual error rate which is sufficiently low. Okay, so far to the FCP. The takeaway from this slide is the FCP ensures that we sample the frame CRC at the right position. Now let's have a look on the CRC concept overview. How does the whole thing look like? And here you see again a MAC frame and with some colors. You see here in blue the pre-phase CRC, and in light blue the area that is protected by the pre-phase CRC. And you see it includes also dynamic stuff bits. In purple you see the FCRC and the area it protects, which is the whole frame before. So it protects everything, but we exclude the dynamic stuff bits, right? So the difference is the dynamic stuff bits here inside. And the dimensioning was done in the following now, to the following values. The pre-phase CRC has a length of 13 bits and provides a Hamming distance of 6 because this is industry standard. And the frame CRC has 32 bits because our payload is so big, we needed the 32 bits, and it also provides a Hamming distance of 6. And by the way, this outperforms Flexray and Ethernet CRC polynomials, and details on that will be given in the next presentation by Dr. Sanger. Now, let's head on to the delta. What is the difference between CANFD and CANXL? In CANFD, error detection was already good, really good. However, we need to get always better, and therefore we have here 5 improvements in CANXL. So we got even better. And this can be summarized in the following. So the first, we added the pre-phase CRC, and this safeguards our data length code. You can see it here, and the data length code is here on the left. So we secure the data length code. And this is easy to do because this is a bit sequence of known length. So the PCRC is always checked at the right position because we know the number of bits here in front. Second, the frame CRC is very powerful now and has 32 bits, and it outperforms even Flexor and Ethernet CRCs. Third, the frame CRC safeguards the preface. That means the preface is double checked. You see this area here in front is just double checked. Fourth, we use fixed stuff bits because fixed stuff bits get us let us get rid of some specific error cases in combination with dynamic stuff bits. So fixed stuff bits are simpler and also make the frame length deterministic. It simplifies the whole system. And finally, we have the format check pattern, which allows us to safeguard the frame CRC sampling. Okay, so far to the summary. Now, let's have a look on the evaluation, because we need to show that it really works. And it's a complex topic, so it takes a lot of time to look at it. And therefore, I want to show you how we proceeded. And since we have so many error types and the frame is so long and there are so many cases, we need a systematic evaluation. And we did the systematic evaluation in the following way. We took all types of errors, so bit flips, burst errors, and bit drops and insertions, and combined it with all possible positions in a frame. And we ended up with a huge table with a lot of conditions, and on the right-hand side, the reasons how the error is detected. So this was a complex table I did, and I presented the results also in the special interest group where the results were reviewed. So this is the way we proceeded, and therefore we are pretty sure that we went through all cases. Now let me show you an example. For example, for burst errors, which is one of the simpler cases, how evaluation works. So let's think about when we remember what, as I showed at the beginning, as I showed at the beginning, we have two types of burst errors. The one burst error, the one type leads to bit flips, and the other one forces the bit values to a constant value. When we take a look at now in the version that causes bit flips, then this may have two reasons. Because one reason may be electromagnetic interference. However, this is very unrealistic. Normally, EMI doesn't lead to flipping bits, right? It leads to a static bus level 1 or 0 and not something that is moving. However, there is a second reason, bit drops and bit insertions. When you have a bit drop, then the receiver sees everything 1 bit shifted or 2 bits shifted. And this feels like bit flips, permanent bit flips, right? If you see something misaligned, then you have a lot of bit flips. However, this check for shifted bit stream is already solved. We have the format check pattern. So this is solved. And additionally, on top of that, the PCR CRC and the FCRC, so the two CRCs we have in the frame, can also detect burst errors of 13 and of 32 bit length. That means we have already several things that can detect these types of burst errors. So this type of burst errors can be considered as solved. Nevertheless, we have a second type, right? The burst error type, which forces the bit value to either 1 or either 0. And now we need to remember that a glitch that occurs doesn't care about the bit rate. A glitch disturbs the waveform, and it depends on the bit rate what this means. When you look on the right side, you see when we have 1/2 megabit, so 500 kilobit, a glitch with the width of this red area here will lead to a bit flip. However, if we go to 8 megabit, you will see this will be a massive burst error because the bits get so short. And now the question is, how can we detect all these cases? Because these are a lot of cases, right? You cannot consider or try all. You need some systematic way to do that. And here is a proof that we can detect all of these errors. So we assume now that any burst length can appear. So we do not constrain the length of the glitch. And we also need to know that in CanXL, every 11th bit is a fixed staff bit. So always after 10 bits, CanXL inserts one fixed staff bit. And the maximum bit sequence then with the same value is 11. So I can have 11 zeros in a row or 11 ones, but never more. And now we have three measures to detect a burst error that can appear. So if the burst error is longer than 12 bits, you see it here, then we can detect it by the staff check or format check. So up from 12 bits onwards, we can detect it because a staff error will occur. If we have fewer, a shorter burst error, then you see both the staff error will detect it, or the frame CRC will detect it also. And if we have even shorter burst errors, maybe only of 8-bit or 9-bit, then the frame CRC and the PCRC will detect it. So there is no way for a burst error to get through because we always have at least two measures to detect it. So the conclusion is all burst errors are detected when we force the bit value to 1 or 0, independent of the bit rate. Okay, so now we saw some details. Now let's take a look at the evaluation summary. So how did this work? As I mentioned at the beginning, we have three types or three mechanisms to detect errors. The format checks, which consist of format check pattern, staff rules, dynamic staff count, frame format bits. Then we have the CRC checks, which consist of prephase CRC and frame CRC. And then we have the bit monitoring, which for sure is only available in nodes which have error signaling enabled. And the first check was done by the following. So the first check, so the evaluation of the format checks was done by myself and was reviewed by the special interest group in CanXL. So a detailed presentation was given, the topic was discussed. Regarding the CRC checks, the generator polynomials were proposed and in detail evaluated by Dr. Sänger from the University of Stuttgart. And regarding bit monitoring, this is a legacy function, so it is well known from CanFD. We don't need any evaluation. This is just a takeover. So we can make a hook there because a detailed evaluation was done. But to be really, really sure, we also did a double checking. And therefore, the University of Kassel worked more than a half year with several people on that topic and double checked the format checks and the CRC checks, and even derived a formula to calculate the approximated residual error rate. And they finished their work end of January this year, and their result was a big green hook. They found nothing that we missed. So a lot of people checked it, and we can now have, from my point of view, a really good feeling because so many people took a look at it. This is no guarantee for sure, but it gives a very good feeling. Now I come to the summary. So what we learned is that CanFD has a good error detection, but it was improved by 5 main measures to get an even better error detection in CanXL. And these are the 5 improvements: prephase CRC, powerful 32-bit frame CRC, double safeguarding of the prephase, fixed staff bits, and format check pattern. And to be really sure that it works, we did a systematic evaluation and a double check performed by Bosch, reviewed by special interest group, CanXL, polynomials proposed and evaluated by the University of Stuttgart, and everything double checked by the University of Kassel. So my message for you today as takeaway from to home is error detection in Can Excel is very powerful. Thank you very much.